Hello dears, in this week we are going to start the design of signal conditioning circuits. So we will start with definition to the signal conditioning, or what is signal conditioning. Signal conditioning is operation done to the signal to put it in a form suitable for interfacing. Like for example, if I want to measure the temperature, starting from the temperature measurement until we keep the signal inside the computer, we are going to go through certain process. What kind of a process we are going to deal with, or how are we going to condition the signals? The first thing, we are going to change the signal range. Signal range is change means the range of the signal or the magnitude of the signal is not high enough to be detected by following circuit. That's why we will amplify it. Amplify it means we put or we make its magnitude higher. Other times the signal is polluted with other unwanted signals. That's why we need to filter it. Filter it means keep the frequencies which we need. The unwanted frequencies we will clear them out. Other time we need to perform conversions. Conversion like what? Like current to voltage conversion, because sometimes we have a sensor which is producing current on its output, but I want this current to be as a voltage so that I can process it. So we need to have a circuit to convert the current to voltage. And also we need to convert resistance to voltage. Sometimes the output of the sensor is resistance, but to process it, I need to convert it to voltage, so we can convert it to a voltage to be able to process it. Amplification, where, as we mentioned earlier, and part of the signal conditioning is amplifying the signal. That means putting it in higher magnitude, or making or producing higher magnitude out of a small magnitude. So the operation amplifier is the device which used for that. The operation amplifier is electronic device which used to amplify the signal, and sometimes we need it to do filtering for the signal. Okay, the operation amplifier has a 3 terminal, 2 inputs and 1 output. These are the terminal for the signal, which we need them for the signal. So 2 inputs, the first one we call it inverting input, and its sign is negative. The other input is non-inverting input with the sign of positive. And the output is shown as the third terminal. The operation amplifier requires DC operation, which called plus minus VCC. So as I mentioned just now, the terminal of the operation amplifier are 3, the main terminal, but still there are terminals not shown here. Another 2 terminals we used to show them here at this position. This is positive VCC and here negative VCC. They are used to supply a power to the operation amplifier by itself. The operation amplifier function, or its operation, it's going to produce on its output a signal equal to the difference between the 2 inputs multiplied into the gain. Okay, so its output is equal to V2 minus V1 into gain. Remember that V2 is the non-inverting input minus the inverting input multiplied into the gain. That's going to be shown on the output. Operation amplifier has a saturation for, or there is limitation for its operation. I mean, we cannot get the operation amplifier amplify the signal to any value. So it's as mentioned here, the operation amplifier has a boundary. It's bounded by VCC. So for example, here the VCC is plus 12 minus 12, which telling me that the output signal cannot be, the output signal here cannot be more than positive VCC and cannot be less than VCC. So yes, the output is equal to the difference between the 2 inputs multiplied into the gain, but it's going to be within the plus minus 12 volt. For the operation amplifier, it's assumed as it's not taking current. The current to its input is almost zero, because it's assumed that its input resistance is extremely high. That's why it takes no current. The operation amplifier are a few types. The amplifier which needed or used in instrumentation. There are a few types. Before I proceed here, let me say something. The gain of the amplifier which mentioned just now, it's permanent. Sorry, it's fixed gain. We cannot change it. But in the circuit, I cannot keep the gain with the same thing. That's why I need to have certain arrangement where I can design the circuit for the gain I want. For that, and also for the application I want. For that, there are 4 circuits we are going to use here in the instrumentation. Actually, there are many circuits for the amplifier, but mainly in instrumentation, we are going to deal with inverting amplifier. I mean a circuit which is going to amplify the signal, and it's going to make it the output shifted by 180 degree from the input. Means positive will become negative and negative become positive. Non-inverting amplifier, it will amplify but not non-invert. Means the input is positive, the output is positive. Differential amplifier is going to make subtraction between the two inputs, so the output is equal to the difference between the two inputs multiplied into a gain which I will make, not the gain of the amplifier by itself. And instrumentation amplifier, which used for instrumentation because it's having higher gain than the others. Instrumentation amplifier, it's going to find the difference between the two inputs, send them to the output, but with very high gain. Let us start with the inverting amplifier. In the inverting amplifier, it's nothing but the operation amplifier which I mentioned just now with this circuit, the circuit of R2 and R1. So R1, or the input signal is sent to the input. Which input is the negative side input, negative terminal. That's why we call it inverting amplifier, because we are connecting it to the negative input. We will see what is the result out of that. So this is to be kept in our mind. Beside that, there is another resistance coming from the output, or connecting the output to the input. So the output connected to the input through resistor R2. We call it R2 or RF sometimes. So whenever I have this arrangement, this is called inverting amplifier. Keep in your mind the positive is to be grounded. Now, why we are calling it inverting again? Because the input having certain sign where the output will be different sign. The input and output shifted by 180 degree. For example, if the input is 5 volt with the gain of the device, the gain of the whole device is let's say 5 millivolt, with the gain of the device something like 2, the gain is 2. What is the output? Output will be minus 2 into 5 means minus 10 millivolt. So when the input is positive, the output is negative. That's what we mean by inverting amplifier. Okay, now we reach to the point where how am I going to make the gain? How am I going to make the gain? The gain of the circuit. The gain of the circuit found to be very easy here in inverting amplifier. It's nothing but R2 over R1. So this is the gain. So notice here the gain AV, sometimes we express it or show it as a AV. It's equal to V out over Vn. Usually the gain is V out over Vn. And in this circuit, it's equal to minus R2 over R1. Minus R2 over R1. This minus means the input voltage and the output voltage are going to be 180 degree shifted. Let us consider this inverting amplifier, which shown here. If R1 equal to 15K, this R1 equal to 15K, and R2 equal to 65K, calculate the output voltage if the input voltage equal to 3.5 millivolts. So if there is a 3.5 millivolt here, what will be the output? So it's very simple. We are going to calculate the gain. The gain formula is saying V out over Vn. equal to minus R2 over R1. So from there we can calculate V out equal to R2 over R1, or the gain, into Vn. So substitute the values, and finally you are going to get the output voltage equal to minus 15.15. How about non-inverting amplifier? Look at the circuit of non-inverting amplifier. You are going to find that the negative side, which we call it inverting input, is grounded through resistance R1, and the input signal applied direct to the positive side, which non-inverting input. And again, there is feedback resistance. We call it feedback resistance, a resistance connecting the output to the input. So that's how the arrangement is. So now this is the input, here is the input, and here is the output. Again, the gain is equal to the output, this output, over input. But I want to know, how am I going to calculate it? How am I going to design it? So it's going to be 1 plus R2 over R1. 1 plus R2 over R1. Or it's the same thing, or it can be written as R1 plus R2 over R1, which is the same thing anyway. So that's the gain of the inverting amplifier. Now, the remaining thing to say is the sign of the input is the same sign of the output. Means if the input is positive, the output will be positive. If the input is negative, the output will be negative. Here is example on the non-inverting amplifier. In this example, he's saying in this figure, if we have R1 equal to 12 kilo ohm, 12K, calculate the value of R2. R2 is missing. We don't know the value. Used in the circuit to produce a voltage of 2.8 volts. So the voltage here is supposed to be 2.8 volt. If the input voltage is 350, if the voltage here is 350 millivolt. So to calculate this one is very simple actually, because we know the formula saying the gain, which V out over Vn equal to 1 plus R2 over R1. So you simply can substitute the known value. The known value are R out and V out and Vn. We also know R1, so it become one equation with one unknown. Solve it. You are going to find finally that R2 equal to 84 kilo ohm. So actually this is very good to learn how to use the amplifier. So I'm using it to amplify the signal. I require certain signal at the output. So how am I going to design the amplifier such that I am getting the output required? The differential amplifier. And the differential amplifier is a combination of inverting and non-inverting. So in the differential amplifier, you are going to find input signal applied to the inverting side and another input signal connected to the non-inverting terminal through resistors with a feedback resistor of R2. So for this circuit, the gain going to look like this. The gain AV is equal to V out over the difference between the two voltages. So the output over the input, but the input in this case is the difference between the two voltages, V2 minus V1, which expressed as R2 over R1. As you see, the quantity is going to be positive here. Positive, of course, if V2 more than V1. Here in this example, we have differential amplifier with the parameter given, R1 equal to 15, R2 equal to 135, R3 250, and R4 equal to 50 kilo ohm. Keep in your mind all in kilovolt, in kilo ohm. Now, calculate the output voltage. This output voltage is needed. If the input voltage V1 equal to 3.5 millivolt and V2 equal to 7.3 millivolt. Okay, so we have the formula which giving us the gain. The gain is equal to V out over Vn. We said Vn is the difference between the two voltages, which given as R2 over R1. So from this formula, we can rearrange the formula to write it as Vout equal to R2 over R1 multiplied into V2 minus V1. So now direct substitution, substitute the values. It's going to be 135 over 15, 135 kilo over 15 kilo multiplied into the difference between the two inputs, and finally it will result in this voltage. So this is the voltage on the output if the two inputs given as you see here. Instrumentation amplifier. In instrumentation, actually, we always hope for the amplifier which having higher gain. So if the amplifier is with high gain, I mean it's stable on high gain, it's going to be suitable for instrumentation, because as I mentioned long time ago, the signal generated by the sensor usually small. So I need an amplifier with higher gain to increase its level or increase its magnitude. So we have instrumentation amplifier which can do this for us. So in the instrumentation amplifier, we can reach up to gain of 1000. So in the instrumentation amplifier, the arrangement is as you see here. You're having a circuit which start with two amplifiers, two circuits with differential amplifier. So it looks like a cascade kind of amplifier. The gain of this amplifier will be AV, the gain, which the output over the input. The output over the input means this output over the input, where the input is two signals. I mean the output over the difference between the two inputs. That's how we can look at it. Is given as R4 over R3 multiplied into 1 minus 2R1 over R2. Look here, R4 over R3, R4 over R3. Remember, this is the gain of the differential amplifier. Multiplied into another gain, which 1 plus 2R1 divided by R2. So that's how we can find the gain of the instrumentation amplifier. Now I want you to keep in your mind that the resistor is not to be taken by its number. We take it by its location. Means if I want to get the gain of this one, it's equal to R4 over R3. That means this resistor over this resistor, whatever its name, whether we call it R3, we call it whatever, it's going to be as simple as this resistor over this resistor multiplied into 1 plus 2 of this resistor divided by this resistor. So whether its number is 1 or 2 or 5 or whatever. That's one thing. The other thing I want you to know that the gain by itself is calculated as seen here. If I want to calculate the gain, this quantity here is known as the gain of this amplifier. This part is the gain of the amplifier. That's how we can deal with the instrumentation amplifier. Now what is remaining is how to deal with it mathematically. Let us see the example in the next slide. In this example, it's very direct question given on instrumentation amplifier, where he gave me the value of R1, R2, R3, and R4, plus or beside that he gave the two inputs V2 and V1. The two inputs are given here to V2 and V1. This is the given elements. He asked me to calculate the gain. The gain from the previous slide, we took the formula, is given as R4 over R3 into 1 plus 2R1 over R2. So by getting, or the formula, from the formula of the gain, we substitute the values as they are direct. So you are going to find that the gain is 25. Now for the second part, you want to calculate the output voltage. the output voltage is equal to the gain into the input voltage. So the gain into the input, which is the difference between the two inputs, will be equal to 780 millivolts.